My name is Edgar Lobaton. I'm a faculty here in the Department of Electrical and Computer Engineering department. And here what we have is our Research Expo, where we have undergraduates and graduate students talking about the different projects related to research. So we're going to start by talking about one of them in particular. So here's Jeremy, and he's going to tell us about what he's working on. Please introduce yourself.
Hey, so I'm Jeremy Coleman, PhD student under Dr. Lobaton. One of the projects that I'm working on is the Kinema project. iBionics Lab is talking about that, so I'll be talking about another project for you guys. This is the Husky project that we have over here. And what we're interested in is autonomous monitoring of construction sites. So what we have is a ClearPath Husky platforms, four-wheel drive robot that has a stereoscopic SAD camera here, LiDAR here, GPS module here, and it's not in there right now, but we also have an IMU that's mounted in the bed of the chassis. Everything is powered by a 24-volt battery. We're using a Jetson to handle the image processing. We have a Raspberry Pi that has ROS on it, handling the motor control for the actuators. So I have a video for you guys, and I guess I can just show you the video. So what you're going to see in this video is the Husky robot moving through a construction site. On the left, you're going to see the construction site. You'll see a 2D representation of that construction site. And then on the right, you'll see the features that we're extracting from the camera feed so that we can localize where the Husky is in the construction site, create this 2D map, and then find out where the Husky is in that 2D map. And this problem is known as a SLAM problem, which is an acronym for simultaneous localization and mapping. Specifically what we're using is Orb SLAM, which is a SLAM algorithm that was adapted for a monocular camera.
It's actually talking about some microscopic fossils called foraminiferous. So let you talk about it.
Okay, I'm Daniel, and basically what we have here is our hardware is consisted of stepper motors, microcontroller, and a programming based on Python that will control the movement. But basically what we're trying to do right now is come up with a locomotion that will allow this to pick a sample of one of these little fossils here and store it according on its classification. Stepper will take care of the microscope, focus. There's going to be a camera implemented to it, and then there's going to be there's going to be 3 axes in total. We have 2 axes. There's going to be 3 axes here, and the motion is basically pick, place, test, store. Then pick next sample, test, and then store. And that's basically what we have. Thank you.
Next, we're going to talk about a project related to smart grids.
Hello, this is Great Works Lab. So we are doing the energy analytics for a smarter energy future. And here is our works. We got the smart meter data, and we do the load disaggregation to reveal how much the baseline energy it is, and also how much the cooling, heating, and the water heater energy is. Then we reveal the energy, how much is used by the HVAC here, and also we replace the old appliances by the new one to find how much energy it can be saved. Then we built on solar PV panels for these buildings. We found out that it needs 21 PV panels to make the energy from the grid is net zero. So this is my work, and also my work of Michael.
Sure. And so on my side, a lot of what I was dealing with was creating a solar array and energy storage sizing tool. And so as you can see, what this takes is it takes a lot of input on your rate structure, as well as load information for the house that you're sizing PV for, and solar information for that house. And then it runs through thousands of simulations for a variety of solar array sizes and energy storage sizes. And it will provide the optimum size of solar arrays and energy storage that will provide the best financial returns in the future.
Next, we're going to be talking about the Cyber Cockroach project, or the Biobots.
Hey, we are the Integrated Bionic Microsystems Lab, or the iBionics Lab, and we are working on biological robots, or Biobots. So the work with Biobots deals with search and rescue. Imagine a building collapses due to an earthquake and survivors get trapped underneath rubble. We are finding out ways by means of which we can rescue those survivors. So these roaches have amazing navigation and locomotor capabilities, and we are borrowing these technologies from nature. And we are using these roaches as beasts of burdens, where we employ our electronic backpacks on the roaches and implant electrodes into their antenna. So for these roaches, if we stimulate their antenna, for example, stimulate their right antenna, they think there is an obstacle to their right and they turn left. In this manner, we can control their direction of locomotion. So after we gain control of the direction of locomotion, we can send in a large number, a swarm of these roaches in the under-rubble area, and with onboard sensors like microphones and buzzers, we can determine their relative positions, and that will help us pinpoint the location of survivors. Information that we can share with first responders and help them save crucial time.